For a very interesting book on transform optics. I was at a conference a couple of weeks ago in Philadelphia, USA, and I met up with Ulf Leonhardt, who's one of the two founders of the field of transform optics. And Ulf was showing me the proofs of his book, which is on transform optics. It's to be published by Dover later this year. It's about 280 pages, costs $25 US, very cheap. He wants mass circulation of this. It's a beautifully written book, so keep your eyes open if you're interested in this topic and get a copy of that book as soon as you can. Personally, I have the ambition to get a copy and start delivering a lecture course out of it. Okay, so it's a very interesting field. And one of the reasons why it's interesting is that it's one of those examples in physics where techniques from one part of physics are actually imported into another part of physics and make it possible to achieve rapid progress. In this case, the importation is coming from the field of cosmology, general relativity, and the methods of general relativity are being applied to the design of metamaterial structures. So, the basic idea for cloaking in the first two papers on the subject, which achieved wide popularity, the two papers were, again, Sir John McPedran co-workers and Ulf Leonhardt, who's from the University of St Andrews. So they considered what would happen if you take a spatial region, you imagine a blob of, say, plastic, and you make a little hole in the centre and you stretch that blob. What you do is that the pinprick that you've made in the centre becomes larger and larger. So they imagine that sort of transformation, and they imagine that this region that you've stretched leaves this hole behind, and that rays of light in fact go through the stretched region but don't get through the hole. Then what you've done is you've created a region which is hidden from electromagnetic waves, and you can hide objects inside that. So this is an idea of taking a region and changing the shape of that region by applying a mapping. So it's a mapping from an old shape to a new shape. And if you apply spatial transformations in Maxwell's equations involve these curl operators. These curl operators have to change when you change your coordinate system. And the way it turns out is that Maxwell's equations are actually preserved under coordinate transformations, except that the properties of the material, which are represented in the new coordinate system, are different from the material properties in the old coordinate system. So instead of, if you start off with a uniform material with an epsilon and a mu, which are scalars, don't depend on direction, don't depend on spatial position, after you've applied your transform coordinates, you find that you've got epsilon and mu, which do change according to direction. So instead of being scalars, they become tensors, and they're also spatially dependent. So you get epsilon ij of x and omega, and you get mu ij of x, the position vector, x, y, z, and omega. So they're functions of position, and they are always functions of frequency. And so this is like the warping of space-time in Einstein's general relativity due to the presence of a black hole or some other massive body. So there are analogies between electromagnetic cloaking and black holes. So this is a diagram from Shurik, Pendry and Smith, Optics Express 2006, one of the early papers on this subject, where on the left, we have a transformation of space, and on the right, we've got these material properties. Okay, so the general principle is that here I've got the grid of space points being transformed. Here I've got a rectilinear grid. These are my new coordinates. If I want to have exactly the same rate paths in the new system as in the old system, but with this new grid, then what I have to have is epsilon and mu functions of position in 2D here. So I'll have epsilon ij of x and y and mu ij of x and y, and knowing the transformation I make to go from here to here, this tells me epsilon and mu in the system. So spatial transformations and transformations of material properties are equivalent and valid points of view. So I remarked about taking my elastic sheet and pulling it apart to create a hole in the middle. That's been done here, and that's created a hole in the middle, and a ray coming along is refracted around the boundary. If you want to create a boundary that rays will not pass through, then what you need to do is create that boundary with a refractive index that equals 0 on the boundary. Refractive index is 0, if you remember Snell's law, will imply that the refracted ray is along the boundary. In other words, you can't get through the boundary. So there are similarities between this style of cloaking and refractive effects in mirages. A mirage, if you've seen a mirage on a hot day, actually is a cloaking of the road surface, because the rays of light seem to have come off a mirror. You can't actually see the road surface through the mirage, because all the rays have been bent by the refractive index gradient and kept away from striking the road. This is a 3D view of that cloaking transformation. We've got the region in the middle where we create the hole in space. We stretch that hole, and that gives us the inner sphere. The outer sphere is the boundary of the cloaking device, where it transitions to free space. So typically epsilon and mu will have gone from 1 here and a diagonal tensor to these values approaching 0 as effectively as you can, to give you a refractive index of 0 around this boundary here. And that refractive index of 0 will take this bundle of rays and actually refract it so that it can never cross this boundary here, but is refracted along. Now, it's a characteristic you require of cloaking that the downstream you see exactly the same bundle of rays as came in upstream. Okay, this is one difference between cloaking and stealth technology. For stealth technology, all you require is that you get nothing reflected back, so that the radar waves aren't reflected. For cloaking, you want this object, this hidden object, not to affect the rays either upstream or downstream of the cloaking system. So these cloaking transformations make a hole in space in which the object to be hidden is placed. Ulf Leonhard wrote a paper in Science 2006 where he considered essentially functions of a complex variable, and this was his cloaking transformation. So his refractive index squared is given by a radius of the cloaked region divided by a singular function. This singular function actually is the stretching of space to stretch space away from this hole in the centre. So refractive index distribution is cloaking the hole at W1. The black circle is the cloaked region, and the range of refractive indices runs out from R0 out to the outer boundary. So the range of refractive indices required goes from 1 down towards 0, and the trick is to be able to get as close to zero as you can. Pretty soon after those two papers, there was a widely publicised experimental confirmation where a theoretical transformation that the experimenters would have wanted to have created in the ideal case is given up the top. So it's a stretching of radius and the theta and z. So this is a cylindrical device. Theta prime and z prime are the same as theta and z, and it's just a stretch in radius. And if you work out what epsilon and mu you need to achieve this, you get this sort of thing. You'll notice that, for example, epsilon theta and mu theta actually go to infinity at the boundary of the cloak. This, of course, is rather difficult to do. In fact, what was built was a simplified device where only three components were played around with, epsilon z, mu r, and mu theta, and this is the equations which were used for that simplified cloak. This is the diagram from that paper of what they actually made. It's a lot better on my computer screen than it is on this overhead screen, so if you want to come in and have a look at it later, you can see it a little bit better, or just look it up in Science 2006. The structure is actually composed of these paperclip-like devices. You'll recognise from what I said before that this is the capacitive part of the design and this is the inductive part of the design to give you those resonances. And what they did to achieve the structuring was that they controlled the parameters of the paper clips as they went inside the structure. So by doing the electromagnetic design, they got this experimental realisation of a cylindrical cloak to behave pretty well like it should have according to theory. This is the diagram from their paper of their experimental results, electric field patterns, and streamlines here indicate direction of power flow. The cloak lies in this green region, and the test object is a copper cylinder which is placed inside the cloaking region, and the main evidence for the cloaking is in fact the repairing of this shadow region which you see with the copper cylinder without the cloak. So this is the structure with the cylinder in place and the cloak in place, and you can see the marked reduction of the shadowing behind the cylinder. This is not a perfect cloak. Nobody claims it's a perfect cloak. It's only a partial cloak. It's a cloak at microwave frequencies, and it's a narrow bandwidth device. It's a 2D device, it's not a 3D device, and it works for only one polarization. So those are very strong caveats, but nevertheless, the publication of this paper created a tremendous furore around the world and excited a lot of people to get into cloaking research. So it's not just cloaking of round objects, you can also do cloaking of square objects. So this is a cloak designed for hiding objects inside a square, and you can see the field lines here. These field lines have a property which is desirable in a cloak. If you look at the field lines here and here, they're virtually the same, and here are virtually the same even when I rotate this object. So this has the property that the cloaking system doesn't disturb the applied field, and the cloaked object is invisible to the applied field. You can have cloaking systems where the cloaked object is hidden, but the cloaking system is visible. Right? So that's also possible. I would regard that as a less perfect form of cloaking, and my colleagues and I gave the name the ostrich effect to the imperfect type of cloaking where you can actually see the cloaking system even if you can't see the cloaking object. And the definition of the ostrich effect is that the large object hides the small object, but the large object does not hide itself. If you can imagine an ostrich in the desert with its head in the sand, then the ostrich has cloaked its head, it hasn't cloaked itself. And you can also do even fancier things. You can create, the analogies with general relativity are profound. You can actually create cylindrical cloaking structures. So this cylindrical cloaking structure will bend light around it as it comes along. If light actually goes through the borehole of the structure, then it's retained inside the borehole. So this structure looks very different from the inside and the outside, so you can do ray tracing simulations of what the universe looks like from the inside of this wormhole and from the outside. So essentially it cloaks outside and it gives you a telescope inside. So it's I remarked before that metamaterials were a very exciting field. This particular collaboration is mathematicians, and they, of course, are very active in this field, as well as physicists, electrical engineers, and other sorts of people. An early example of transformation optics was applied for a very different purpose. This is some work we did with French collaborators in 1979. Our object was actually solar energy research. We were interested in whether we could make metallic surfaces of, say, silver or gold or other materials appear very black to instant radiation. If you've got a metallic surface with bumps all over it, it's quite challenging to model electromagnetically. You've got an instant wave coming in and it has to interact with all these bumps. So the colleague of mine, Graham Derrick, who was first author on this paper, was an expert in general relativity. He said, why don't we just map this bumpy surface onto a plane surface, then we can calculate what this metallic interface does to the fields very easily. So we did that, and the equations are generic. These are the sort of equations which also apply throughout transformation optics. You take your original coordinates where you've got Maxwell's curl equation saying that curl of E is proportional to H and curl of H is proportional to E. In this case, there's the square of the refractive index there, and that refractive index is spatially constant except when you jump interfaces between different materials. You can transform that any way you like with a coordinate mapping. That coordinate mapping is like the coordinate mapping in Einstein's general relativity, and there's a metric transform GLM, there's a metric transform with GLM, and there's another one with G superscript L superscript M. Those two are different but easily related, and they actually give you transform Maxwell's equations. I remarked that Maxwell's equations actually remain the same under transformations. They do remain the same, except for these factors which come from the transformation, this 1 on square root determinant of this matrix, and then there is this GIL here, and similarly here. So these equations actually tell you how to change Maxwell's equations if you're taking space and stretching it, or taking space and compressing it, or creating some sort of wobble board with space on it. These are the equations which you use to deal with transform optics. And the GIL, the metric tensor, comes naturally from your equations for relating the new and the old coordinates. So what we gained from this transformation was that we made the boundary conditions crossing the surface trivial to implement. The thing that we got out of it was that the medium above the surface was replaced by an inhomogeneous anisotropic media, and that's given by the metric tensor of the coordinate transformation. So in effect we had to put these equations on a computer and we could solve them, but we got very accurate solutions of these structures, and it was the first time they had ever actually been investigated or solved. I remarked earlier that cloaking is different from stealth technology. Stealth technology, of course, is a field where a lot of research was done but not published over the period of the Cold War, and it then is related to the modern field of cloaking, but the aims of the two different fields are narrower. Stealth technology is all about avoiding radar detection, or in the case of submarine, sonar detection, and typically you've got an emitter and it's looking for reflections off an object. So all you're concerned about in stealth technology is avoiding reflection. The aim of cloaking technology is that Harry Potter is invisible regardless of the direction from which you observe him. So it's always been the aim that the whole thing works over the entire range of angles. That's one of the differences between stealth technology and cloaking. Cloaking is for all angles. The wavelength range, typically you know the radar frequencies that various people use, and typically the wavelength ranges of radar sets are much narrower than the wavelength range in visible light. So again, cloaking is more ambitious in its frequency or wavelength range. The technique of stealth technology, of course, a couple of things are done, shaping the aeroplane or the submarine to avoid reflections. So you avoid having mirror-like objects which can reflect strongly. So the whole thing is composed of angles which tend to reflect without bending rays back on themselves. The other thing you can do where you can't avoid reflection is absorb the probe radiation. So the lecture from the Russian I referred to, they were actually coating inside jet engines with these absorbing coatings, because the jet engines are one area where you get strong reflections. So both of those are highly advanced technologies. They're unrelated in that cloaking tends to be taken not very seriously by the military people, because they realise the problems of actually making it work over the full bandwidth of visible radiation. I've referred to this before. The stealth technology from Russia was based in part upon Veselago's work. I myself have done some work on cloaking by an entirely different mechanism. You'll have observed that the sort of cloaking that Pendry and Leonhard and a lot of other people work on actually creates a cavity in the cloaking system, and you hide objects inside the cloaking system. The sort of resonance cloaking I've been working on is called exterior cloaking, because it actually, you take a cylinder in this case, and it's got a core and a shell, and you actually choose the material of the shell so it has a resonance with either the core or the matrix material outside it. I won't go too much into the detail of this. This was published in 1993 and in later papers building upon that 1993 paper. But the physics is rather peculiar and interesting. As I said, you get resonances when the permittivity of the shell plus the matrix adds up to 0, or when the core and the shell permittivities add up to 0. Now, when those resonances actually occur, the coated cylinder actually behaves like a solid cylinder in electrostatics. So, in the case of a shell core resonance, then the resonance actually makes the core appear as if it goes right out to the outer boundary of the shell. If you have a shell matrix resonance, then what happens is that this equivalent cylinder, which behaves like the core region, actually has got radius RS squared on RC, so that is actually larger than either of the radii in the cylinder. So the cylinder behaves in what you might call a homeopathic way, in that the coated cylinder behaves like a solid cylinder, and the smaller the core region, the larger the equivalent cylinder. Homeopathy is a branch of alternative medicine where people believe that taking very small quantities of poisonous substances can make them much healthier. Has to be carefully controlled, naturally enough. It's believed that Rasputin was a practitioner of that art. Hence the difficulty in poisoning him, if you know the history of Rasputin. So there's a peculiar consequence of this, that if you've got a coated cylinder and a source outside it, then you can solve that problem by a method of images, and you get an image source inside. Now, if this were the coated cylinder behaving like a very large object, then it can be the case that this source created by imaging is actually in free space rather than inside a material medium. And in fact, you can show that this is equivalent to Sir John Pendry's perfect imaging. And the other thing that can be done with this is cloaking, and you can use this for a cloaking mechanism, which I'll now show you. The mechanism for the cloaking, as I said, the coated cylinder creates an invisibility region outside it. And in that invisibility region, what happens is, if you've got an applied field and you've got a particle you're wanting to hide, the person looking for that detection of that hidden particle is applying an electric field to try and visualize it where it is and what it's made of. What happens is that that person applies the electric field, and there's an interaction between that applied electric field and the coated cylinder, and that interaction actually cancels out the applied field where the particle is. So this is a reaction between the applied field and the particle, so that the particle, which is outside the cloaking system, is hidden from external electric fields. So I'll just show you an animation from the Optics Express paper. This Optics Express paper was in 2007, and it contains various animations showing this cloaking process. If you want to actually go to the Optics Express website, you can download all of these animations. The cloaking radius in this case is given by the square root of the cube of the shell radius divided by the core radius. This is the cloaking radius in the animation. What you have approaching that coated cylinder is a set of 7 dipoles arranged in a hexagon. There is an applied field, and this applied field reacts strongly with the 7 polarizable dipoles when they're outside the cloaking region, and I'll just show you what happens when it moves inside the cloaking region. So this is one of the animations from that paper which you can download if you're interested. So what you actually get is this violent reaction between the applied field and the coating and the cloaking cylinder whenever this set of polarizable particles is inside the cloaking region. As the particles actually emerge from the cloaking region, the phenomenon stops. Just to show that again, you get these resonances, you get these colossal fields building up, and these colossal fields actually cancel out the applied field acting on the polarizable dipoles, so they become invisible. You can see that throughout this interaction, there is no disturbance of the applied field outside the cloaking circle as long as there's cloaking. All you can see then is the polarizable dipoles here. this cloaking system is always invisible. So this is a perfect cloaking system from the point of view of avoiding that ostrich effect. So, so this is another alternative cloaking system. As I said, it's a 2D cloaking system. It's based on electrostatic, so it requires long wavelengths. We have worked on that for shorter wavelengths, and we've studied it under interaction effects under cloaking particles. We had hoped that we could use whole systems of these coated cylinders, and we could tune each of them to a slightly different wavelength to improve our bandwidth. But in fact, there were interaction effects which occurred under systems of cloaking particles which worked in exactly the wrong way from our point of view. What happened was, if we had several cloaking systems and an applied field, and then this particle to be cloaked entered, in fact what happened was that the cloaking systems tried to cloak each other and they ignored the particle to be cloaked. So interaction effects in this were a problem, and so it remains an interesting phenomenon which we're interested in extending to spheres. The problem in this sort of cloaking is it doesn't require structured materials, that's its advantage, but it does require you to have the shell of these cylinders made of some material which has got a permittivity equal -1. You'll remember that Sir John Pendry, for his perfect lens, also required epsilon equals -1 and mu equals -1. This sort of cloaking requires just one of the two. Nevertheless, it's difficult to achieve in practice. Okay, so that concludes what I want to say about cloaking. If you look at the literature of cloaking, there are hundreds, literally hundreds of papers on the subject written every year. Some of them experimental, some of them theoretical. There are a recent flurry of activity was connected with what was called hiding under the carpet cloaking. And the idea of that was, suppose you have a mirror and you have a bump on that mirror, then you can hide something behind the bump on the mirror, but of course you want the bump on the mirror to be invisible, therefore you can create a structure which actually hides the bump on the mirror. I would regard that as not a particularly good form of cloaking because the bump on the mirror is hidden, but the mirror itself is not hidden. So that's the sort of cloaking which is subject to the ostrich effect. So the real challenge, I think, is to take the Pendry, Shuriken, Smith or Leonhard designs and make them work wide bandwidth in the visible range. Whether that is feasible or not remains to be seen, but certainly there are convincing demonstrations at longer wavelengths than visible. Well, thank you for your attention. I've enjoyed lecturing to you, and of course I'm open for questions and any discussions over lunch break.
Questions?
Yeah.
If you're inside the cloaked object, is there any way to look actually outside of this object, or because you shouldn't see anything, right? Because or you would be seen, or is there any way you could look outside actually without being seen?
Okay, that's a problem also which arises in stealth technology. One of the things in stealth technology is that you tend to get reflections off the canopy where the pilot looks out of the cockpit. So the way the Russians got around that was they had a special coating on the canopy, and that coating was normally non-reflective, but when they the coating was normally absorbing, so you couldn't look out at it, but if you needed to look out of it, there was a laser which would actually shine on the material and change its properties so you could look out of it. That's one thing you can do. So you can actually change the properties of the system using non-linear effects, interaction of some electrical or optical signal to enable you to look out. Secondly, you can, one of the things that actually goes on in these cloaks, for example, the sort I showed you, you saw that tremendous reaction between the applied field, the body to be cloaked, and the cloaking system, and gigantic fields were created. So if you're actually inside that cloaking system, then all you have to do is measure a tiny fraction of the fields, and you know that somebody's looking for you. So to that extent, you can actually take your cloaking system and build sensors into it, which will enable you to look outside. But it's actually one of the features of cloaking systems is that a perfect cloaking system will make the object inside it blind to the wavelengths which you're trying to bend around the object. So yeah, perfect cloaking, if it could be achieved, would result in blindness.
So in the case of the super limit, is there still something, can you find something like a numerical aperture, or is there some other fundamental limit that will, like a wavelength dependent fundamental limit that will tell you what your best resolution is, or?
Well, what happens in reality is that the resolution is limited by the loss in the material making up the lens. You can never actually make a material with epsilon equals -1 perfectly. For example, silver, there is a wavelength where the real part of epsilon is -1. It's around about 0.34 microns, okay? But unfortunately, the imaginary part of epsilon is around about a half. So it's quite absorptive. So that in fact limits the resolution, but there are experimental verifications that with silver structures you can achieve super resolution, a factor of say 2 or 3 better than the Rayleigh limit. So that of course has been done. People are interested in actually overcoming this problem of loss. There's a recent set of papers on what's called a spacer, S-P-A-S-E-R, which is a device where you actually have metals around, but you actually create fields which interact with the metallic fields and add energy to them. So there is hope that we may be able to overcome the loss in metals. If you look up spacers, you'll find a couple of papers late last year. Very, very interesting field. People who are keen on spacers say it could be the equivalent of a laser. Yep.
It's possible to get the metamaterials or cloaking in your white band, the broadband, multiple wavelengths.
The best bandwidth ever demonstrated for cloaking is in work by Zhang from Berkeley, who demonstrated this hiding under the carpet cloaking. If you believe that that's cloaking, then that's the widest band demonstration. The bandwidth demonstrated for that was around about 1.3 to 1.8 micron. So it wasn't in the visible because of the lithography requirements, but it was wideband. That's very strong wideband operation. It's non-resonant, it was a pure dielectric structure. So the cloaking device, and this illustrates the convergence between photonic crystals and metamaterials I was talking about. The cloaking device in the Zhang experiments, what they put on top of the mirror with a bump on it was essentially just a distorted photonic crystal. And the reason why it's wide bandwidth is because it doesn't involve metals. So if you believe that that's a form of cloaking, then it's white bandwidth. Yes?
There were some recent works on using purely dielectric metamaterials like based on Lie resonances.
Based on what?
Lie resonances.
Yes. There is work on yes. There's a whole lot of work in this area, and various concepts are being floated. There's a lot of interest in materials which aren't metamaterials to the extent that they are not interested in controlling mu. All they're interested in is controlling epsilon. And this group of metamaterials or structured materials are structured so that they have epsilon, which is very close to 0. And that gives you, they call it ENZ metamaterials or structured materials. And they give you very interesting properties. So they give you incredibly narrow waveguides, for example. So you can confine light through these incredibly narrow channels and not suffer reflections with the ENZ. That's again, it's difficult to get that wide bandwidth, but that's some very promising work. You can also do the equivalent of plasmonic resonance, but with dielectric structures, and then you're choosing the coating to try and cancel the reflection off the sphere. Okay, so again, that's been done by Ngega and his group at the University of Pennsylvania, and by Andrea Alou, who's now at University of Texas Hospital. So there's an awful lot of work. As I said, there are hundreds of papers published on this field every year, so I'm not about to summarise them or even read them all. But there are international conferences on the subject. For example, there's one in Karlsruhe later in the year.
So one more question. According to the definition which you gave previously, if they don't have magnetic response, they cannot be called metamaterials.
Yes.
Photonic crystals.
That's one definition. That's one definition. That's a strict definition. I think it's a useful definition because otherwise it becomes very hard to distinguish photonic crystals from metamaterials. There's also the other characteristic that it should be structured much finer than the wavelength. But in fact, people rarely achieve that experimentally, so that's not so useful.
Well, you mentioned that similar phenomena have been demonstrated also for other waves, including human waves in water.
Yes.
So when you have this unusual behavior,
Yes.
should we think about the systems exhibiting these behaviors, metamaterials too? Although in those cases you wouldn't have magnetic properties playing in.
But you have the equivalent. For example, I've worked on phononic band gaps. And phonons are elastic waves in structured materials. And in this case, you have different sorts of waves. You've got shear waves and bulk waves. And you've got to control both of them. So the analogy of a metamaterial is, in that field, would be a structure which can control both shear waves and bulk waves. I've done some work recently on what we call platonic crystals, and these actually are thin structured plates, hence platonic. In that case, you can have up to 3 different types of waves propagating. So essentially, the concept is of being able to control all the sorts of waves or wave properties relevant to that particular structure. But if it only involves a single type of waves, then it's probably better described as an equivalent of a photonic crystal rather than that material.
How does the polarization of the visible light affect the efficiency of the cloaking? I mean,
How's the what?
polarization of the light. I mean, does it work for unpolarized as well?
Polarisation of light, if you're dealing with cylindrical structures, it's very strong. These cylindrical structures only work for one particular polarisation of light. Okay? If you want polarisation independence, then you probably have to go to systems with cubes or spheres, isotropy. Okay? So you have to have isotropic cloaking. And that's much more difficult. Most of the field is still talking about cylindrical 2D type cloaking because of the fabrication problems. But everybody really wants to work towards cubic or spherical systems, lattices with cubic symmetry, so that we can get bulk materials with metamaterial type